So good morning. I have the okay to start. Good morning to everyone. It is my honor to open this session on quality of life, sponsored by the Harridge Institute on Aging. And before introducing our first speaker, I would like to briefly present 2 slides about the Harridge Institute on Aging. So our institute was established in 1992 at Tel Aviv University. The Institute fosters interdisciplinary research as evidenced by the joint direction of the Faculty of Social Sciences and the Faculty of Medicine. We conduct and promote a broad range of studies relating to age and aging, and in addition to this main goal, we also try to disseminate the knowledge on the field of aging, both in the community and the academy. And we provide information to health policymakers. Studies conducted by researchers at the Harridge Institute concerns issues such as physical and mental health, health promotion, well-being and quality of life, cognitive and emotional aging processes, dementia, caregivers and caregiving. And our research approach is multi-level, going from person to society, integrated biopsychosocial approach, and we use diverse research methods. Our leading principles in our research are high scientific standards. We support young researchers and encourage them to engage in the field of aging. And overall, instead of talking about burden and cost of aging, we see aging research and promotion of health in all ages as an investment for tomorrow. Information about the Harridge Institute can be found in our website, and you can see here the address. And now, it is my pleasure to introduce our first speaker, Professor Stephen Harridge, head of the Center of Human and Applied Physiological Sciences at the King's College London. Professor Harridge is interested in many aspects of physiology, and specifically in physiology of skeletal, muscles, and aging. And today we are going to hear about declining performance of athletes, the trajectory of healthy human aging. Professor Harridge.
Thank you very much, and good morning, everyone. It's a great pleasure to be here virtually. Very disappointed, obviously, not to be with you in person. But thank you very much for inviting me. And I'm hopefully going to put this on slideshow mode now. Great. Okay. So thank you. What I'm hoping to do in the next 15 minutes is perhaps challenge some perceptions of aging by talking about the population of individuals who represent the physiological elite, shall we say, of the aging population. Before I do that, I'm just going to acknowledge the collaboration of my close friend and colleague, Professor Norman Lazarus. We've been working for many years on all aspects of aging. Recommend his interesting book, How to Age Well and Wisely. But I just want to acknowledge that things I'm presenting today are really the joint efforts of both of us. So if we want to understand more about the biology of human aging and its effect on physiological function, which model do we use? And of course, there are multiple models, some of which here have been applied in my lab to the study of skeletal muscle and aging. We can study cellular senescence, we have critical illness, microgravity, and of course, this disease model, progeria. And when we talk about skeletal muscle, which has been my prime research interest over the years, we're primarily concerned with the loss of muscle mass and loss of function. The term sarcopenia, introduced about 30 years ago, describes how we lose muscle function. It's described here on the left. As we grow, we become stronger, and reach a peak in sort of our early adulthood, and then we have this progressive decline to a point where we could be in real trouble. We're unable to move effectively, and we lose our ability to move and function independently, and we're at increased risks of falls and sustaining hip fracture and so on. And the reasons underpinning this loss of function pertain primarily, but not exclusively, to the loss of skeletal muscle mass. And what you're looking at here in these 2 images are MRIs of the mid-thigh So you can see the femur here. This is a 31-year-old healthy woman. This is an 85-year-old healthy but sedentary woman. And you can see in terms of the gray matter, this loss of tissue mass, not only that, but an infiltration of fat and connective tissue. And there are multiple processes that are involved, and we still don't have an identifiable cause of sarcopenia. One of these potential causes is this concept of inflammageing, the fact that we get chronic low-grade inflammation. I've got two examples here of IL-6 and TNF-alpha observed comparing healthy but sedentary older individuals compared with healthy younger. We can see these elevated inflammatory factors, and I'm going to come back to that a little bit later. So in my lab, we've been trying to understand more about human muscle aging. We've been using critical illness models. We've been using unloading or microgravity models. We've also have a cell biology program, all with this idea of trying to understand more about the aging muscle mechanisms underpinning its phenotype. But does this really represent true biological aging? And this is where I'm going to switch focus to talk about the importance of aging and exercise in our understanding of biological aging processes. So I'm going to go back to Hippocrates here, 400 BC. That which is used develops, and that which is not used wastes away. If there's any deficiency in food or exercise, the body will fall sick. Now, I think those are pretty wise words, said 400 BC. More recently, Joseph Barcroft from UCL said, exercise is not a mere variant of the condition of rest, it is the essence of the machine. More recently, Frank Booth, our genes evolved with the expectation of requiring a certain threshold of physical activity. Thus, being physically active is the evolutionary default position for maintaining good physiological function. So being active is what the body is designed to do. And of course, the vast majority of all populations are doing insufficient levels of physical activity and exercise. So we could create this model here where we look at, are we studying aging or the study of older people? And we can have two ends of this continuum here. People who are sedentary, have poor nutritional intake, often smoking, drinking to excess, and so on. At the other end of the spectrum, we've got people like this who are highly active, in this instance, still competitive athletes. But of course, many studies of aging, primarily because we're trying to discover how we can help older people as we progress through to things like frailty and so on, they err in the direction of these individuals rather than these exercising individuals. But if we want to study biological aging, then we're in trouble, because inactivity is deleterious to health, it contaminates many of our studies of aging, and confounds our understanding of the real aging process. We kind of need a health warning on studies of aging. Norman and I have published a number of articles in regards to that concept. So now I'm going to move back to 1925 to A.V. Hill, Nobel Prize-winning muscle physiologist, but also one of the world's first exercise physiologists. And he said, in the study of the physiology of muscular exercise, there is a vast store of accurate information in the records of athletic sports and racing. So we apply that concept to looking at aging. So what we're looking at now are the world record performances on the track of 100 meters and the 10,000 meters for both males and for females. And we can see that in these individuals who represent the best possible performance that's been achieved as a ratified world record over the track 100 meters and the 10,000 meters, as I said, with increasing age. We work in 5-year age increments in masters or veterans athletics. And you can see there's this progressive decline in time. So everyone's getting slower in irrespective of event, till we get around sort of the mid-70s-ish, when there's this break point or an acceleration of decline. Now we can apply that to multiple other sports. So here we have examples of swimming, for example, where we see the decline in performance given in slightly different terms, but it actually shows very nicely the break point again occurring, where there's an acceleration of decline over age 70. So they've got this interesting performance decline, but what does this break point suggest? And I'm going to come on to this in a second. But also these curves are very interesting because, one, we have a relatively limited base of older athletes. They are cross-sectional data, And of course, older athletes may not have been exceptional young athletes. So in that, I'm going to show some very interesting data from one individual. This is the world record holder for the long hurdles. It actually becomes the 300-meter hurdles after age 60. This Guido Müller, he is able to, he is actually the world record holder for each of the age groups here. But interestingly, as well as showing a progressive decline up to age 70, he is also showing this breakpoint. So when he hit the 75-year age record, he showed a marked acceleration in the decline. And just to put it into context, I've added Carsten Warholm, who broke the world record this year at the Tokyo Olympics for 400-meter hurdles. That's where he cuts here. So whilst these are incredibly remarkable performances from the older athletes, we can see that there is still this decline in function. But this is representing aging. So what we've got here is a model that Norman and I produced in introducing the concept of the set point theory of exercise. And that being a slight extrapolation of the set points that we have in physiology in regard to blood pressure, core temperature, and so on and so forth. But it's basically saying, look, there's a certain amount of exercise or physical activity that each one of us needs to do to be able to age healthily. We're in the green zone, effectively. Above that, you're in the realm of being a master athlete, but below it, where so many people are, we're doing insufficient activity, we compromise our health span, and we have an uncertain health trajectory. We have non-optimal aging. Whereas in the green zone and above, we optimize the health span, compress morbidity, and have an optimal aging process underway. So I've redrawn this graph from the elite athletes. So we're showing this breakpoint in performance time. And the hypothesis here is saying that any person who is exercising at set point, who undertakes a performance test every 5 years, which is a 5-kilometer run, will show the same shape of decline. So in other words, if we have not an elite athlete, but someone who's just a regular exerciser performing that test, that individual, or indeed another person with different ability, will show the same shape of decline as the elite athletes themselves. The absolute times are irrelevant, and the question then is, actually, are these curves a reflection of the trajectory of our innate decline in integrative physiological function as we age? So to study the biology of healthy human aging, we must exclude those in the red zone and only study those are at or above the green zone. Otherwise, we are interacting aging with inactivity processes. And when we do that, I'm going to show you some studies that we've been performing at King's. This is one we published in 2015, where we studied a group of individuals who were clearly at or above the green zone. And we were trying to understand something about their physiological phenotype. And we studied a group of non-elite, but they were amateur road cyclists. And we had some quite strict entry criteria. So for a male, for example, he had to be able to cycle 100 kilometers in under 6.5 hours. So clearly above what we would expect the green zone to be. And within that, we measured a whole bunch of things that did a deep physiological phenotyping, and I haven't got time to go into all the things that we did, but the cyclists were aged between 55 and nearly 80 years of age. When we just looked at their muscle, and we took muscle biopsy samples from each of these individuals, and the key point here is that we actually saw none of the indications of a sarcopenic muscle in the older participants. So in other words, the muscle fiber morphology was really nice. We saw no infiltration of fat or connective tissue. Histopathologists will identify this as coming from a young muscle. And indeed, when we look at MRIs from these particular individuals, this is a cyclist aged 83, we see no evidence of the decline that we're seeing as a typical sarcopenic muscle. Now, we're not the only individual or the only groups that are looking at this. This is a group in Italy, and what they studied here is mitochondria. So what we're looking at here are the mitochondrial fission and fusion proteins. I'm not going to go through what they are. Suffice to say, it's a typical response that we might expect. And then we compare young with the old. There is a decline in these mitochondrial proteins, which are important for fusion. This is the typical story. There's an age-related decline. However, when we look at individuals who are highly active in that group, in the red bars here, we see that in fact, not only are they not showing the decline, but they seem to be superior to the young. If we look at another model of muscle, if we look at single fiber mechanics, so this is the muscle force being produced by an individual muscle fiber studied in vitro, taken from either young, shown in black bars, or to the right of that, older individuals, and these are for type 1 slow twitch muscle fibers or type 2 fast twitch muscle fibers. You can see that there is no difference between the young and these endurance athletes, but as we increase the level of inactivity in these older individuals, I should also emphasize that these are over 70 years of age, these endurance athletes, and all these other participants are over 70 years of age. But with increased inactivity and increased immobilization, we see that there is this decline. So again, depending on whom we study, we would draw completely different conclusions about the aging process. One of the key variables that we're interested in was maximal oxygen uptake. This is the index of cardiorespiratory fitness. We can see here that the decline in maximal oxygen uptake is progressing as we get older. Well, that's nothing new. What's new about that? Well, new about this is the fact that all these individuals were highly active. We cannot ascribe this change to a decline in levels of physical activity because they were all highly active. And when we normalize the data to body weight, the males and females become closer to one another. But the key point here is I've put a slope of, from a meta-analysis of a sedentary male population. So you can see the cyclists are up and to the right. If we were to, for example, take an 80-year-old cyclist and see where their value hits the sedentary slope, we can see that they are equivalent to a sedentary person 35 years younger. So that's a 35-year functional advantage that these active older people have compared to the young. Or we turn that around and say, actually, it's the older cyclists who are where they should be. They are on the correct slope for their age because they're optimizing physical activity. It's the young individuals who are the ones who are not where they should be. So they're the ones that have a 35-year functional disadvantage or have accelerated their aging process. Just very quickly, in collaboration with Janet Lord and Harrica Duggal at the University of Birmingham, we studied immune function. We published a couple of years ago, very topical at the moment in terms of COVID, but the bottom line being that we had superior immune function across numerous indices. If we compare our master cyclists with a healthy but sedentary cohort, we can see that in terms of the percentage of T cells here, they're identical to the young, with both the young and our cyclists being superior compared to the healthy old. And there are numerous other indices that I could go through. So we have, coming back to this concept of inflammageing, if we now look at our master cyclists in terms of IL-6 and TNF-alpha, we can see that they are markedly different to the sedentary old. So these are the healthy young. Compared to the healthy old, we have our master cyclists who have a marked amelioration of that inflammation. So this concept of inflammation is linking to this concept of cellular senescence and our interest in senolytics, and evidence is emerging that exercise itself is anti-inflammatory and is a natural senolytic. And indeed, this is a very nice paper highlighting the complexity and why we're interested in exercise, because exercise is universal, it's global, activating multiple signaling pathways across multiple systems, and then here has been described as the real polypill. So going forward, and if it hadn't been for COVID-19, I'd hope to be able to show you some data of what we're doing now, in that we are retesting all of our master cyclists, who we first studied in 2012, 2013, in a longitudinal study. So this is shown here in the green. So these are green ages. We're performing a longitudinal study on this particular cohort, but with the funding that we've got from the Darchi JetBrains Foundation, we also have three additional groups. We're studying a group of sedentary older individuals, sedentary young individuals, and active young cyclists to complete this matrix. So we have a longitudinal study here, but also a cross-sectional design in the same laboratory. We're using multi-omics platforms to try and tease out the effects of aging from inactivity-related processes. So I'm very conscious of time, so I will summarize by saying aging is the natural biological process, which is generally reflected in a decline in physiological function. But many features of aging are also impacted by inactivity-related processes. So in the majority of older people, what we're seeing in terms of physiological function is an interaction of aging and inactivity. When we study the most vigorous of exercise, namely our master athletes, we can see that function still declines. But the key point is they have much higher levels of physiological function, have an extended health span, as well as compressed morbidity. But what we really need to do is remove the effects of inactivity by studying people who exercise. That way we can get insights into the inherent biological and healthy aging process, free from the contaminants of the inactivity processes. So I'll leave with this quote: we don't stop playing because we grow old because we stop playing. I think, again, that's really pertinent from George Bernard Shaw, a non-physiologist. I'll just acknowledge the Healthy Aging Research team at King's. So that was our team completing the 100K cycle from London to Brighton about 5 weeks ago, ranging in age from 24 to 86 years of age. So thank you very much for listening, and I'm very happy to take any questions.
Thank you very much, Professor Harridge. Fortunately, we don't have time for questions, so we will move to the next presentation, and our next speaker